This is an audio file on the project, a fully integrated membrane bioreactor system for wastewater treatment in remote applications. It's SERDP project number ER2237. This audio file was created on April 12, 2019. I am Amy Childress, professor at the University of Southern California and principal investigator on this project. My co-PIs were Andrea Achille of the University of Arizona, Sage Heibel and Eric Marchand of the University of Nevada, Reno, and Chan-Woo Park of the University of Missouri. Sachi Dash assisted with monitoring, controls, and optimization. An integrated osmotic membrane bioreactor membrane distillation system, or OMBR-MD system, was designed, fabricated, and tested at the pilot scale for wastewater treatment and production of high-quality reuse water. There were very clear synergies in using MD to reconcentrate the draw solution used in the OMBR process, in using low-grade heat to drive the MD process, and in recovering heat from the distillate solution to reduce the overall heat consumption of the system. The abundance of low-grade heat produced by diesel generators at forward operating bases makes the OMBR-MD system an ideal system for such locations. During long-term OMBR operation, carbon and nitrogen removal was achieved in a single reactor by alternating between aerobic and anoxic bioreactor conditions. Results from long-term testing using a high-strength wastewater showed 98.4% removal of chemical oxygen demand and 90.2% removal of ammonia as nitrogen. Physical design aspects and process controls for system integration, as well as procedures for wastewater treatment with the single-stage OMBR system, were established. Several areas for improvement were also identified throughout the development and testing phases of the system, namely passage of some dissolved low molecular weight contaminants into the closed-loop forward osmosis MD solution led to MD membrane fouling and reduced MD water flux, and over time, the ammonium concentration in the distillate solution tended to increase. A suggested improved design draws upon this and other lessons learned during the current project. Ammonium passage into the distillate solution could be mitigated by improved biological ammonium removal, in other words, nitrification or denitrification, in the OMBR. To accomplish this, it is suggested to configure the OMBR with a dual chamber tank with separate oxic and anoxic zones. Aeration in the oxic zone would be optimized for nitrification and membrane cleaning. The anoxic zone would be optimized for denitrification. The revised OMBR-MD system would operate in a semi-batch configuration defined by two separate process loops. One loop would operate the OMBR and the other would operate multiple MD modules. Each loop would operate individually until two triggering conditions are met. First, the draw solution reaches a target dilution value in the OMBR loop, and second, the MD feed solution reaches a target concentration in the MD loop. Once the triggering conditions are met, the solutions in each loop would be exchanged. The diluted forward osmosis draw solution would then be treated by MD, and the concentrated MD feed solution would then be diluted by forward osmosis. This semi-batch process scheme would allow for independent and continuous operation of the forward osmosis and MD loops, reducing the complexity of the necessary control mechanisms to maintain steady-state operation of this dynamic continuous process, and thus implementing a simplified operation that maximizes the performance of each process. Once the tank switch occurs, the diluted draw solution volume would pass to the MD loop and undergo further treatment through a fine screen, a cartridge filter, a carbon filter, and an ultraviolet reactor to reduce the possibility of membrane fouling, membrane damage, or passage through the MD membrane by small organic compounds or disinfection residual. The suggested revised system would be programmed to periodically backwash the forward osmosis membranes to extend membrane life and improve performance. The backwash cycle would utilize a portion of the distillate stored in a standalone tank. When forward osmosis performance is degraded, or after a predetermined time period elapsed, the system would cease normal operation and change to the necessary valve configuration to route the distillate to the forward osmosis module. Backwashing in a counterflow regime reverses the impact of fouling and scaling that occurs over time on the forward osmosis membrane. The used backwash solution would be further treated with MD to maximize water recovery. Regarding the MD subsystem and based on testing subsequent to development of the current OMBR MD system, it is suggested to consider use of an air gap MD module in the revised system instead of the direct contact MD module that is used in the current system. This research led to the publication of 6 journal papers with 3 additional papers in review or submission, as well as numerous conference proceeding papers.